Here we have a triple integral from 0 to 1 of the integral from 0 to 1 minus x squared of the integral from 0 to 1 minus x, f of x, y, z, dy, dz, dx. And what we're going to do is we're going to rewrite it as an equivalent iterated integral in the 5 other orders. If we permute dy, dz, dx, there are 6 possible orders. We've been given one of them, and we have 5 others that we can use to represent this integral. As you can see, we have a figure that represents the region that's given by the limits of integration. And what we've got here is the parabolic cylinder z equals 1 minus x squared, and it's in the first octant, and it has been sliced by the plane y equals 1 minus x. So we basically have this wedge. The first order that I'd like to use is the one where we just switch the dz and the dx. So we're going to use the order dy, dx, dz. dy is the innermost differential, and it's the innermost integral, and that's not one that's changing, and so its limits won't be affected. So for the innermost integral, it's still the integral from 0 to 1 minus x of f of x, y, z. We have to have that there even though we don't know what the function is, dy. But then what we're switching is the dx and then the dz, and it's up to us to figure out the limits for x that can or cannot be in, or may not be in terms of z, but cannot be in terms of y, because by the time we get to dx, we will have already integrated with respect to y. From the integral that was given to us, dz is the middle differential, and we see that that is associated with limits of integration from 0 to 1 minus x squared. Writing that as an inequality, we have that z is between 0 and 1 minus x squared inclusive. In order to switch the order to dx dz, what we need to do is take the implied equation z equals 1 minus x squared and solve it for x. We will end up with x is equal to the square root of 1 minus z. As far as the lower limit for x, we can see that in the original integral that we were given, all 3 variables have 0 as their lower limit. So we have, for limits of x, 0, and then the square root of 1 minus z. And then for limits of z, we can see that for this region here, z goes from 0 to 1. That gives us the iterated integral from 0 to 1 of the integral from 0 to the square root of 1 minus z, of the integral from 0 to 1 minus x, f of x, y, z, dy, dx, dz. Now let's consider dz, dy, dx, and dz, dx, dy. Based on our diagram, we can see that z has a lower limit of 0 and an upper limit of the parabolic cylinder. So we can say with confidence that z will go between 0 and 1 minus x squared, and that'll be true for both of these orders that we just wrote down. Now that we've dealt with z for dz, dy, dx, let's look at the y portion. For that, I'm going to look at the triangular region in the xy plane, and I can see that y goes from 0 to the line y equals 1 minus x. So y goes between 0 and 1 minus x, and then I see that x goes from 0 to 1. So this would be the integral from 0 to 1 of the integral from 0 to 1 minus x of the integral from 0 to 1 minus x squared of f of x, y, z, dz, dy, dx. For the order dz, dx, dy, we note that we go back to the triangular region in the xy plane, but we pretend we didn't do what we just did. And we can see that x goes from 0 to the line y equals 1 minus x, which means that x will go from 0 to 1 minus y. Solving that equation, y equals 1 minus x for x. And then we can see that y goes from 0 to 1. So this is the integral from 0 to 1 of the integral from 0 to 1 minus y of the integral from 0 to 1 minus x squared of f of x, y, z, dz, dx, dy. And these two integrals are equal to each other. All we're doing is changing the order of integration. For the orders dx, dz, dy, and dx, dy, dz, it is a little more tricky in this case. If we imagine that we were standing somewhere in the first octant near the positive x-axis, looking at the projection onto the yz plane, we would note two things. Number one, the trace in the yz plane appears to be a 1 by 1 square. But we would also note that there's a diagonal kind of cutting through the square, and it's the edge of, that's the intersection of the parabolic cylinder and the plane. And we're going to have to consider that actually separately. Here's what I mean. Here's the 1 by 1 square in the YZ plane. And what I'd like to do here is color the kind of the faces that we're looking at. The plane y equals 1 minus x, I'm going to represent using green highlighting. And then the parabolic cylinder, I'm going to represent using, it looks purple, but I swear it's pink, highlighting. This translates into the projection onto the YZ plane has kind of an arc going through it from the upper right corner to the lower left corner. Below the arc, we would see the green face if we were standing here in the first quadrant. Above the arc, we would see the pink parabolic cylinder. I swear that is pink. You buy that, right? Like you buy that this pink here is this pink here. I don't need to make this purple, do I? What this means is that for dx, dz, dy, we're going to have two integrals that we're going to add together. One of them is basically related to the green portion in this square, and one's related to the pink portion in this square. And likewise for dx, dy, dz, we're going to have basically a green iterated integral that we're going to add to the pink iterated integral. Let's start with dx. In the green portion, x goes from 0 to the line or the plane that has the equation y equals 1 minus x. But we would rewrite that equation and say that x is equal to 1 minus y. So in the green portion, x goes from 0 to 1 minus y. Let me move that over. And that's true for both orders, right? X isn't going to change when we change the order of dz, dy. So for both of them, x goes from 0 to 1 minus y. For the pink portion, you can see I've already drawn it here. X goes from 0 to the parabolic cylinder, z equals 1 minus x squared, which we're going to rewrite as x is equal to the square root of 1 minus z. So for the pink portion, x goes from 0 to 1 minus z in a square root. X goes from 0 to the square root of 1 minus z. Now for the order dx, dz, dy, let's go ahead and finish off the green portion and then we'll jump to the pink one. Z in this region here in the xy, or the projection in the, I said xy, the projection in the yz plane, we can see that for the green portion, z goes from 0 up to the dividing line here, the dividing curve. Well, that curve comes from the parabolic cylinder. So what I would want to say is that z goes from 0 to 1 minus x squared. However, I can't have z depending on x if I've already integrated with respect to x. The relationship that we have between x and y is that x is equal to 1 minus y. Therefore, we've got that z, I've got to replace x. Z is going to go from 0 to 1 minus the quantity of 1 minus y squared. Simplifying, we get that z goes from 0 to 2y minus y squared. And then we can see again that y goes from 0 to 1. So that gives us one of that pair of integrals from 0 to 1 of the integral from 0 to 2y minus y squared of the integral. At this point, I'm reading these in the reverse order, how we wrote them. That third integral is the integral from 0 to 1 minus y of f of x, y, z. And then the order that we were working on was dx, dz, dy. To that, we're going to add the integral that we get from analyzing the pink portion. We're still working on the order dx, dz, dy. We've already figured out the limits on x. Now we need the limits on z. Z goes from the curve up to 1. That curve, we already decided in terms of y, is 2y minus y squared. So z is going to go from 2y minus y squared to 1. And then y again goes from 0 to 1. So to the green iterated integral, we add what we just got from the pink one. The integral from 0 to 1 of the integral from 2y minus y squared to 1 of the integral from 0 to the square root of 1 minus z squared. The integrand is still f of x, y, z, and we use the order dx, dz, dy. Now we turn our attention to the order dx, dy, dz. We already know the limits on x for the green portion. For y, we can see we go from this curve to 1, but that curve is defined by this plane, right? It's the curve of intersection between the plane and the parabolic cylinder. Therefore, I would want to say that y goes from 1 minus x to 1. However, y can't depend on x if we've already integrated with respect to x. We need x in terms of z, and we have that. X is equal to the square root of 1 minus z. Therefore, y goes from 1 minus the square root of 1 minus z to 1. And we can see that z goes from 0 to 1. And so the first iterated integral for the green portion here is going to be the integral from 0 to 1 of the integral from 1 minus the square root of 1 minus z to 1 of the integral from 0 to 1 minus y of f of x, y, z, dx, dy, dz. To that, we're going to add the iterated integral that represents the pink portion. At this point, I'm going to go ahead and put boxes around my answers because, well, first of all, it's good form. And I think I'm about to run into a problem presenting the answer there, because it would have been difficult to see what was going on with all of these triple integrals. Now, for the pink portion, for dx, dy, dz, we already have the limits on x. We need the limits on y. For the pink portion, y goes from 0 to the curve. That curve we've already dealt with. So we see that y goes from 0 to 1 minus the square root of 1 minus z. And then we can see that z goes from 0 to 1. So the pink iterated integral is the integral from 0 to 1 of the integral from 0 to 1 minus the square root of 1 minus y of the integral from 0 to the square root of 1 minus z f of x, y, z, dx, dy, dz. Put a box around it, and now we have our 5 iterated integrals.